The universe is missing a trillion ghosts. Every second, trillions of neutrinos from the Big Bang should be flowing through you, yet they have seemingly vanished. This is one of the greatest detective stories in modern physics, and by the end, you will understand how this cosmic disappearing act might rewrite the rules of reality. We will uncover why the Sun seemed to produce too few of these particles and explore the bizarre phenomenon that explains where they have been hiding all along. What do you think it takes to catch a ghost? To catch a ghost, you first need to understand its nature. This particle is called the neutrino. It is so ethereal that it can pass through light years of solid lead without a single interaction. It carries no electric charge and has almost no mass, making it the closest thing to nothing that something can be. The story of its discovery begins not with a sighting, but with a crime scene. Physicists in the early 20th century were studying a type of radioactive decay called beta decay, and they found something deeply troubling. Energy was vanishing from the system. It was as if a bank robber had stolen money from a locked vault without leaving a single fingerprint. The great physicist Wolfgang Pauli proposed a desperate solution. He suggested an invisible particle, one that could carry away the missing energy without being seen. He even apologized for his own idea, calling it something no theorist should ever do. He had invented a particle that could not be detected, a ghost. This ghost, the neutrino, was eventually proven real decades later. But its very nature, the qualities that make it so elusive, are the very reasons its disappearance now poses such a monumental puzzle. If you cannot see the thief, how do you know if some have gone missing? The first undeniable crack in our understanding appeared deep underground in a gold mine in South Dakota. Here, physicist Ray Davis built one of the most audacious experiments ever conceived. His goal was simple and nearly impossible. He wanted to catch neutrinos from the Sun. His detector was a colossal tank filled with 600 tons of a common cleaning fluid. The idea was brilliant. On the incredibly rare occasion a solar neutrino interacted with a chlorine atom in the fluid, it would transform that atom into a radioactive form of argon. Davis' painstaking work involved extracting and counting these handful of argon atoms each month. It was like trying to find a few specific grains of sand in an entire beach every single day. For decades, he collected his data, and for decades, the results were deeply unsettling. His detector was catching only about 1/3 of the neutrinos that our best models of the Sun predicted should be arriving. This was the birth of the Solar Neutrino Problem. The numbers simply did not add up. Either our entire theory of how the Sun shines, a process called nuclear fusion, was catastrophically wrong, or something very strange was happening to the neutrinos on their journey to Earth. The core of the Sun, where these particles are born, seemed to be working perfectly. We could see the light and feel the heat, proving fusion was happening. So the blame fell on the ghostly particle itself. The neutrinos were leaving the Sun, but they were not arriving at Earth in the numbers we expected. It was as if a factory was working at full capacity, shipping out its products, yet the delivery trucks were arriving at their destination half empty. Where were the missing particles? This was not a small accounting error. It was a fundamental warning that our grasp of physics was incomplete. The universe, it seemed, was playing a trick on us, and the solution would be even more bizarre than anyone dared to imagine. The solution arrived not from the Sun, but from the very fabric of reality itself. For decades, physicists were trapped in a single, flawed assumption. They believed a neutrino was born as a single, static identity, an electron neutrino from the Sun that would forever remain an electron neutrino. This was the core of the problem. Ray Davis' detector was only designed to catch one specific type, the electron neutrino. The breakthrough came when theorists proposed a truly bizarre idea. What if neutrinos were not stable identities but cosmic chameleons? What if they could spontaneously change from one type to another as they flew through space? This phenomenon was called neutrino oscillation. Think of it like this. Imagine you send a pure beam of green light on a long journey. Midway, you check it and find it has mysteriously transformed into a mix of red and blue light. By the end of its trip, it has shifted back to mostly green. This is the essence of oscillation. A neutrino born in the Sun as an electron type could, on its way to Earth, temporarily become a muon or tau neutrino before changing back again. Davis' experiment was only sensitive to the original electron flavor. It was blind to the others, so when the neutrinos oscillated into their other forms during the 8-minute journey from the Sun, his detector registered them as missing. They were never gone, they were just in disguise. This radical idea demanded proof, and it came from a remarkable facility in Japan called Super-Kamiokande. Deep inside a mine, a colossal cylindrical tank holds 50,000 tons of the purest water, lined with over 10,000 golden eyes, sensitive light detectors that watch for the faintest glimmers in the dark. This experiment did not rely on chemical transformations. Instead, it watched for the faint blue flash of Cherenkov radiation, a light shockwave created when a neutrino, on the rarest of occasions, interacts with an atom in the water. Crucially, Super-K could distinguish between the different neutrino flavors by the pattern of light they produced. The data was undeniable. They could see muon neutrinos coming down through the atmosphere from cosmic rays above, and they could compare them to those coming up through the Earth from the atmosphere on the other side of the planet. The ones that traveled the longer distance had more time to oscillate, and sure enough, fewer of them arrived as muon neutrinos. They had changed into a flavor the detector could not see at that moment. This was the direct, irrefutable evidence. The discovery that neutrinos oscillate was so profound it earned the physicists behind it the Nobel Prize. It solved the solar neutrino mystery, but in doing so, it shattered a fundamental pillar of the standard model of particle physics. Oscillation proved without a doubt that neutrinos must have mass. This was a revelation that shook physics to its core, opening a door to a universe far stranger than we ever imagined. But this revelation of oscillation forces us to ask a deeper question. What exactly is changing? The answer lies in the 3 distinct identities or flavors that a single neutrino can cycle through. Think of it as a single actor who can only play one of 3 specific roles at any given moment. The first and most famous is the electron neutrino. This is the star of our solar story, born in the immense nuclear furnaces of stars like our Sun. Every time protons fuse together to create helium, releasing the light that warms our world, electron neutrinos are produced as a fundamental byproduct. The second flavor is the muon neutrino. These are not born in the calm fires of stars, but in the violent chaos of the upper atmosphere. When high-energy particles from deep space, cosmic rays, smash into air molecules, they create a shower of secondary particles, including muons and their associated muon neutrinos. The third and most elusive is the tau neutrino. It is often created alongside its heavier sibling, the tau particle, in the most energetic collisions, such as those inside particle accelerators or from cataclysmic stellar explosions. Each flavor is a unique character tied to its own specific kind of cosmic drama. The key to the great disappearance is that a neutrino is never locked into just one of these roles. A neutrino born in the Sun as an electron neutrino does not simply stay that way for its entire life. As it travels through the emptiness of space, its very identity becomes unstable. It begins to oscillate, morphing seamlessly into a muon neutrino, then into a tau neutrino, and then back again. This is not a gradual shift, but a constant, rapid flickering between all 3 possible states. This is why Ray Davis saw only a third of the expected neutrinos. His detector was built to recognize only one actor, the electron neutrino. But during their 8-minute journey, the solar neutrinos were spending most of their time playing the parts of muon and tau neutrinos, roles his equipment was completely blind to. They were not missing, they were simply on stage performing in a costume he could not see. So the next time you feel the sun on your skin, remember that 1 trillion ghosts are passing through you every second. Most of them are just wearing very clever disguises. So how do you build a trap for a particle that can pass through a planet as if it were empty space? You must think in extremes. The hunt for neutrinos is a story of engineering on a staggering scale, designed to find a signal in a universe of noise. The first challenge is to escape the constant cosmic radiation raining down on Earth's surface. That is why these detectors are buried deep underground, inside mountains or at the bottom of mines. These layers of rock act as a natural shield, blocking out everything but the ghostly neutrinos. Then you need a target, an enormous amount of material to increase the infinitesimal odds of a collision. Ray Davis used 600 tons of cleaning fluid. The Super-Kamiokande and Detector in Japan holds 50,000 tons of ultra-pure water. But the grandest trap of all lies at the South Pole, a project called IceCube. It transforms a cubic kilometer of ancient, pristine Antarctic ice into the world's largest scientific instrument. Engineers melted 86 holes deep into the ice sheet, lowering over 5,000 sensitive light detectors on long strings, creating a grid that spans a volume of over 1 billion tons. This is the scale required to catch a ghost. The magic happens on the incredibly rare occasion when a neutrino does interact. It might strike a proton in the water or ice, creating a new particle like a muon that travels faster than light can move through that medium. This creates a faint, eerie blue glow known as Cherenkov radiation. It is the optical equivalent of a sonic boom, a shockwave of light. In the absolute darkness of these subterranean or sub-ice tanks, thousands of golden sensors wait to capture this fleeting blue flash. Each one is a digital eye staring into the void for a spark that may only come a handful of times a day. The data from these flashes is then used to trace the neutrino's path, its energy, and even its flavor. It is a painstaking process of counting the uncountable, of building a cathedral to observe a shadow. Every flash of blue light is a victory, a moment when the most elusive particle in the universe reluctantly announces its presence. Yet our sun is a relative newcomer in this cosmic story. Far older and more numerous are the primordial neutrinos, the ghostly echoes of creation itself. Just as the universe cooled from the Big Bang, it left behind a faint afterglow of light known as the cosmic microwave background. But a full second before that light was set free, the universe forged another, even more ancient relic. This is the cosmic neutrino background, a sea of particles so vast it defies comprehension. These are the very first neutrinos, decoupling from the primordial soup when the cosmos was just 1 second old. They have been streaming through the universe ever since, untouched and unchanged for over 13 billion years. For every proton in the universe, there are roughly 1 billion of these relic neutrinos. They are everywhere, a cosmic fossil whispering secrets from the dawn of time. But if they are so numerous, why have we not found them? The challenge is one of unimaginable subtlety. These ancient neutrinos carry incredibly low energy, having been cooled and stretched by the expansion of the universe itself. They are the quietest ghosts in a sea of louder, more modern specters. Detecting them is the ultimate goal, a feat that would allow us to peer directly into the universe's first second of life. It would be like listening for a single, faint heartbeat in the roar of a hurricane. Finding this background would confirm our most fundamental theories about the Big Bang and reveal how these elusive particles shaped the formation of the very first galaxies. So the question is not just where the sun's neutrinos went, but where the universe's first ghosts are hiding now. They are all around you, 1 trillion passing through your hand with every beat of your heart, their faint story still waiting to be heard. The quietest sound in the universe is the one we most desperately want to hear. These relic neutrinos from the Big Bang are not just elusive, they are fundamentally different from the ones we catch today. Modern detectors like Super-K and IceCube are built to find high-energy neutrinos, the ones born in stellar explosions or particle accelerators. These particles arrive with a punch, creating a clear, detectable flash of light. But the ancient cosmic neutrino background is a whisper in comparison. After 13 billion years of the universe expanding and cooling, these primordial ghosts have been stretched to energies a billion times lower. They are so feeble that they simply do not have the strength to trigger the reactions our current experiments rely on. It is the difference between trying to hear a pin drop in a quiet room and trying to hear that same pin drop from the other side of a city during a thunderstorm. The signal is not just weak, it is drowned out by a universe of background noise. Every radioactive decay from the rocks around a detector, every stray cosmic ray that penetrates the deepest shields, creates a false signal that masks the faint signature we are searching for. We are surrounded by a sea of these ancient particles, yet they pass through our most sophisticated traps without leaving a trace, their story untold because we lack the ears to listen. To capture such a faint whisper, we need a completely new kind of ear. This is the goal of a proposed experiment called Ptolemy, the Ptolemy Project. Its design is as brilliant as it is audacious. Instead of waiting for a relic neutrino to interact randomly in a vast tank of water or ice, Ptolemy aims to force an interaction by making the neutrino collide with a specific, rare type of hydrogen atom. The core of the detector would be a flat, frozen sheet of tritium, a radioactive form of hydrogen. The idea is that when a relic neutrino strikes a tritium nucleus, it would be absorbed, transforming the nucleus in a unique way that scientists could then measure. This is not about catching a fleeting flash of light, it is about capturing the ghost permanently and weighing the evidence it leaves behind. The challenge is almost beyond belief. The detector would need to be kept at a temperature within a fraction of a degree of absolute zero, the coldest possible temperature in the universe. It would need to be so utterly pure and so exquisitely sensitive that it could distinguish the unique signature of a single relic neutrino interaction from the constant buzz of tritium's own natural radioactive decay. The experiment would essentially be listening for one specific, quiet note in a symphony of static. Success would be one of the greatest achievements in the history of science, a direct line back to the first second of everything. It would prove that these foundational ghosts are real, allowing us to test our theories of the Big Bang in a way that was previously just a dream. So while we now understand the disguises of the sun's neutrinos, the universe's oldest ghosts remain just beyond our grasp, a silent chorus waiting for the day we finally learn their song. This tiny, almost imperceptible mass is the key that unlocked the entire solar neutrino mystery. For decades, the standard model of particle physics, our most successful theory of the fundamental building blocks of the universe, insisted that neutrinos were massless. They were supposed to be ethereal spectators racing through the cosmos at the speed of light, forever unchanged. But the phenomenon of oscillation, the very thing that explained the missing solar neutrinos, proved this foundational idea was wrong. Neutrino oscillation is only possible if these particles have mass. Think of it like this. Imagine three different runners, one light and swift, one slightly heavier and stronger, and one built for endurance. If all three weighed exactly nothing, they would run at the exact same impossible speed and could never change places. But if they each have even a tiny, different weight, their paces will vary minutely. Over a long enough distance, the subtle differences in their stride will cause them to shift positions relative to one another. The runner who started in the lead might fall behind, only to catch up again later. This constant, rhythmic shifting is what we call oscillation. The neutrino's mass, however small, creates these slight differences in their quantum mechanical rhythm, allowing them to cycle through their three identities. Without mass, they would be frozen in a single state, and Ray Davis would have seen the full expected number from the sun. Their ability to change disguises depends entirely on them not being perfect ghosts, but having just a whisper of substance. So how much mass are we actually talking about? The numbers are almost comically small. The total mass of all three neutrino types combined is less than 1/1,000,000th the mass of the next lightest particle, the electron. If an electron were a small mountain, a neutrino would be a single grain of sand. This incredible smallness is why they were thought to be massless for so long. We now know they have mass, but we do not know exactly how much. This is one of the most pressing questions in physics today. Pinpointing the precise masses would not just solve a curiosity, it would reshape our understanding of the cosmos on the grandest scales. These tiny weights influence how galaxies cluster together and how the universe has expanded over billions of years. Experiments across the globe are now trying to weigh the unweighable. Some, like the Katrin experiment in Germany, study the endpoint of a specific type of radioactive decay with unparalleled precision, looking for the subtle imprint a neutrino's mass leaves on the energy of the reaction. Others look to the cosmos, mapping the large-scale structure of the universe to see how the gravitational pull of these trillion-fold ghosts has subtly sculpted the distribution of galaxies. Each experiment is a high-stakes race to measure the immeasurable, to put a number on the shadow. The mystery of the missing neutrinos led us to a profound truth that even the most elusive particles in existence carry a tiny anchor of reality. And that anchor might just be the thread that pulls us into a deeper, darker universe. This tiny anchor of mass pulls us toward an even deeper cosmic mystery. Why does anything exist at all? In the first moments of the Big Bang, energy should have condensed into equal amounts of matter and antimatter. These opposing kinds of particles are destined to annihilate each other on contact, vanishing back into pure energy. If the universe had been perfectly symmetrical, every particle of matter would have met its antimatter twin, and the entire cosmos would have dissolved into a featureless sea of light. There would be no stars, no planets, and no us, yet here we are in a universe made almost entirely of matter. Something must have tipped the scales, creating a tiny, 1 in a billion excess of matter over antimatter. That tiny excess is everything we see. The question of what broke this fundamental symmetry is one of the greatest puzzles in all of science, and the answer might lie with our ghostly friends, the neutrinos. The leading theory is called leptogenesis. It suggests that in the searing heat of the early universe, extremely heavy, right-handed neutrinos began to decay. Now, this is where it gets truly strange. For this process to create the matter imbalance we see, neutrinos would have to possess a bizarre and unique property. They would have to be what physicists call Majorana particles. A Majorana particle is its own antiparticle. For most particles, this is impossible. An electron has a clear opposite, the positron. They are a distinct pair, but if a neutrino is a Majorana particle, then there is no difference between a neutrino and an antineutrino. They are one and the same. This self-annihilating identity is the key. In the early universe, the decay of these heavy Majorana neutrinos could have proceeded just slightly differently for particles versus antiparticles. Through a process known as CP violation, these decays would have produced a tiny but crucial surplus of matter over antimatter. Every other particle annihilation then wiped the slate clean, leaving behind only that small surplus of matter that the neutrinos had created. According to this theory, every atom in your body, every star in the sky, is here because of a subtle preference in the decay of a ghostly particle that is its own opposite. We are the leftover evidence of a cosmic preference for existence. The hunt to prove this is now underway. Experiments like the Legend project, located deep inside an Italian mountain, are searching for an ultra-rare nuclear process called neutrinoless double beta decay. If observed, it would be the smoking gun, proving that the neutrino is indeed its own antiparticle. It would mean that these phantoms are not just cosmic chameleons, but the ultimate paradox, a fundamental particle that is its own mirror image. Finding this would do more than just solve a mystery. It would rewrite our origin story, revealing how the universe used the most elusive particle in existence to conjure something from almost nothing. But the story of the neutrino may be even stranger than three flavors. What if there is a fourth ghost, one so elusive it makes the others seem loud and obvious? This is the speculative yet compelling idea of the sterile neutrino. Imagine a particle that is so detached from reality it does not even feel the weak nuclear force, the very faint interaction that allows our three known neutrinos to occasionally announce their presence. A sterile neutrino would be blind to everything except gravity. It would be the ultimate phantom, whispering only to the fabric of spacetime itself. The motivation for such an outlandish idea comes from persistent, unexplained glitches in the data. Certain experiments, particularly those studying neutrinos from nuclear reactors or radioactive sources, have recorded a curious excess of particles at specific energies, a bump in the data that does not fit the clean picture of three oscillating flavors. One interpretation is that some of the known neutrinos are briefly oscillating into this fourth, sterile state, a hidden realm we cannot directly detect. When they oscillate back into a regular flavor, they appear in our detectors as an unexpected surplus. It is as if a magician we thought only had three hats was secretly using a fourth, invisible one, and we only notice when the rabbit pops out. If sterile neutrinos are real, they could account for a portion of the universe's most profound missing pieces. Their substantial mass compared to regular neutrinos and their sheer abundance could make them a perfect candidate for dark matter, the invisible gravitational glue that holds galaxies together. We have been searching for dark matter for decades, looking for exotic, undiscovered particles. It would be a profound twist of fate if the answer was not a new kind of monster, but a quieter, more ghostly version of a particle we already know. The hunt is on to confirm or dismiss this phantom. New experiments are being designed with unprecedented sensitivity, searching for the subtle distortions in neutrino oscillation patterns that would betray the sterile neutrino's shadowy influence. Finding it would not just add a new particle to the list, it would tear open a hidden door in the universe, revealing a whole new layer of reality operating just beyond our perception. A dying star broadcasts its final moments through these silent messengers. When a massive star exhausts its nuclear fuel, its core collapses under its own immense weight in a matter of seconds. This catastrophic event, a core collapse supernova, unleashes one of the most violent explosions in the universe, and neutrinos are at the very heart of the drama. As the iron core crushes down to the density of an atomic nucleus, protons and electrons are forced together, merging into neutrons and releasing a staggering flood of neutrinos. In that single spectacular detonation, a supernova can release more energy in neutrinos than our Sun will emit in light over its entire 10 billion year lifetime. For about 10 seconds, the dying star shines brighter in neutrinos than all the stars in the observable universe combined. This is the primary way the star sheds its gravitational binding energy, a ghostly scream announcing its own death. But how do we know this is truly what happens? We have witnessed it once in an event that astronomers still speak of with awe. In February of 1987, a star went supernova in the Large Magellanic Cloud, a nearby galaxy. It was the closest observed supernova in nearly 4 centuries, visible to the naked eye. But the light, traveling across 168,000 light-years, was not the first signal to arrive. Hours before the visible explosion lit up the skies, 3 neutrino observatories around the world registered a pulse. Over a span of just 13 seconds, 24 ghostly particles were caught. This might not sound like a lot, but it was a bonanza. For the first time, we had direct evidence of the core collapse process itself. The neutrinos had raced ahead of the shockwave, escaping the cataclysm just moments before the star tore itself apart in a blaze of light. Their detection was a perfect match for our theoretical models, a triumphant confirmation that we truly understand the furious engine at the heart of a stellar explosion. These events are neutrino factories on a cosmic scale, and each one contributes an immense number of new ghosts to the cosmic population. Every supernova that has ever occurred has flooded the universe with these particles, adding to the trillions that are already flowing through you from the Sun and the Big Bang. They are the cosmic couriers carrying news of stellar death across the vast, empty distances of space. So while we search for the quietest whispers from the beginning of time, we must also listen for the deafening shouts from the death of stars. High above our heads, an invisible rain is constantly falling. Cosmic rays, which are high-energy particles from distant supernova and other violent cosmic events, slam into the upper atmosphere at nearly the speed of light. When they collide with air molecules, they shatter them, creating a shower of secondary particles. In this chaotic debris field, new particles are born and quickly decay, and among their products are muon neutrinos. These atmospheric neutrinos pour down upon the Earth from every direction, a steady drizzle of ghosts from the sky. For physicists, this created a perfect natural experiment. They realized they could use the entire planet as a laboratory. Think about a detector like Super-Kamiokande buried deep inside a Japanese mountain. It can see atmospheric neutrinos coming from two distinct paths. Some come straight down from the atmosphere directly above, traveling a relatively short distance to the detector. Others are produced on the exact opposite side of the planet, so they must travel all the way through the Earth to reach the detector from below. This journey takes thousands of miles and a fraction of a second longer. If neutrinos were truly stable, unchanging particles, the number coming up from below should be roughly the same as the number coming down from above. But the data told a different story. The detector saw a clear deficit of muon neutrinos arriving from below. The longer journey through the Earth had given them more time to oscillate. Some of the muon neutrinos had simply transformed into tau neutrinos, a flavor the detector could not see at that specific moment. This was the first unequivocal, man-independent proof of neutrino oscillation. It was not happening just in the Sun, but right here in our own atmosphere, a constant, silent metamorphosis. This discovery locked in the solution for a huge part of the missing neutrino problem, proving that the ghosts were not vanishing, they were simply changing their masks on the fly. Nuclear reactors offer a controlled glimpse into the neutrino's shadow world. While the Sun is a natural fusion reactor, our own power plants on Earth are prolific factories for a different kind of ghost. In the process of nuclear fission, as heavy elements like uranium split apart, they produce a predictable cascade of radioactive decay. A key byproduct of this decay is a steady, calculable stream of antineutrinos, the antimatter counterparts to the particles from the Sun. For decades, physicists have placed detectors near these powerful sources to count the arriving antineutrinos. The results were eerily familiar. Just as with the solar neutrinos, the reactors were producing fewer antineutrinos than our most careful calculations predicted. The deficit was not as large as the one from the Sun, but it was undeniably there. Once again, the ghosts seemed to be vanishing between their origin and our detectors. This reactor anomaly pointed to the same bizarre conclusion. The antineutrinos were not disappearing, they were oscillating, changing into flavors that the nearby experiments could not see. To put this theory to the ultimate test, scientists needed to create a grand experiment, one that could watch this transformation happen over a known distance. The answer was found in the mountains of Japan with an experiment named CAMLAND. Imagine a detector placed at the center of a vast web, with over 50 nuclear power plants surrounding it from every direction. CAMLAND was that central point, listening to the combined hum of antineutrinos from reactors across Japan. On average, these man-made ghosts had to travel about 180 kilometers to reach the detector, a journey that gave them just enough time to oscillate. The Camland detector, filled with 1,000 tons of liquid scintillator, watched for the faint flashes of light created when an antineutrino interacted. The data was a perfect mirror of the solar neutrino solution. Camland saw only about 60% of the expected reactor antineutrinos. The pattern of this deficit precisely matched the predictions of oscillation over that specific distance. It was the final, beautiful confirmation. The same physics that explained the missing ghosts from our sun also explained the missing ghosts from our power plants. This was not a problem unique to the stars. It was a universal rule of nature, proven here on Earth with human-made particles. The reactor neutrinos closed the loop, demonstrating that oscillation is the fundamental, chameleon-like nature of these phantoms, whether they are born in the fires of a star or the heart of a machine. This cosmic chameleon act has implications far beyond our solar system, touching the fate of the entire universe. We now face an even deeper puzzle, one involving the very fabric of space and the energy hidden within it. The universe is not just expanding, it is accelerating, pushed apart by a mysterious force known as dark energy. Its nature is perhaps the greatest enigma in all of cosmology. Yet to understand its power, we must first account for every other form of energy in the cosmos, including that carried by the lightest, most numerous particles of all. The sea of relic neutrinos from the Big Bang, for all their ghostly subtlety, is so vast that its combined energy density becomes a significant part of the cosmic ledger. Every cubic centimeter of space holds hundreds of these ancient particles. While a single neutrino carries almost no energy, multiply that by the unimaginable volume of the observable universe, and their collective weight becomes a force to be reckoned with. They contribute to the total energy budget that shapes how the universe expands and evolves. For decades, cosmologists have tried to balance this budget, comparing the total mass and energy we can account for against the observed effects of gravity and dark energy. The relic neutrinos are a crucial, though faint, line in that ledger. Their confirmed presence and estimated mass help us pin down the numbers, narrowing the possibilities for what dark energy could be. But what if the connection is more direct? Some theorists propose a breathtaking idea. What if the properties of neutrinos are not just a line in the budget, but are intrinsically linked to the mechanism behind dark energy itself? One speculative but compelling thought is that the same quantum fields that give neutrinos their tiny masses might also be responsible for the energy inherent in the vacuum of space. This vacuum energy, often called the cosmological constant, is the leading explanation for dark energy. It is the energy of empty space itself, a constant push against the pull of gravity. The puzzle is that our simplest calculations of this vacuum energy produce a number that is catastrophically large, one that would have torn the universe apart in its first moments. The observed value of dark energy is incredibly small and finely tuned. So why is the universe's acceleration so gentle? The answer might involve a cancellation effect, where the contribution from known particles like neutrinos almost but not perfectly cancels out other, larger contributions. The subtle mass of the neutrino and its interaction with the Higgs field or other unknown fields could be the key player in this cosmic balancing act. It is as if the universe is a delicate mobile, and the neutrinos are the smallest, final weights that bring the entire structure into a precarious, beautiful balance, allowing for the slow acceleration we see today. The ghost that solved one cosmic disappearance may yet hold the clue to the greatest expansion mystery of all. This faint blue flash in a polar ice sheet might be our only message from a supermassive black hole. While light can be absorbed or scattered by cosmic dust and gas, neutrinos travel in a perfectly straight line from their violent birth, carrying an unaltered story of the events that created them. This makes them the ultimate cosmic messengers, especially for the universe's most extreme phenomena. Consider an active galactic nucleus, the heart of a distant galaxy where a supermassive black hole weighing billions of times our Sun is actively feeding. As matter spirals into the abyss at nearly the speed of light, it forms a searingly hot accretion disk and often launches jets of plasma stretching for millions of light years. The processes deep within these jets and disks are hidden from our telescopes, shrouded by the very matter that powers them. But neutrinos, born in the heart of this maelstrom, fly straight out. When one is finally caught by a detector like IceCube, its path points directly back to its source, offering a clean, unedited view into the engine of a cosmic monster. Similarly, gamma-ray bursts, the most powerful explosion since the Big Bang, are thought to be factories for ultra-high-energy neutrinos. These bursts, lasting from seconds to minutes, can outshine an entire galaxy. The prevailing theory is that they are caused by the collapse of a massive star into a black hole or the merger of two neutron stars. In either case, the event likely produces a narrow, ultra-fast jet of particles. The physics within that jet is where the highest energy protons are accelerated, and when they collide with other particles or light, they can create neutrinos. If we can catch these neutrinos and correlate them with a gamma-ray burst observed by satellites, it would be like getting a blood sample from the patient while also watching the explosion from the outside. It confirms the internal mechanics of the blast. This is the ambitious goal of multi-messenger astronomy, where we combine different cosmic signals, light, gravitational waves, and neutrinos to build a complete picture of a single event. By mapping the arrival directions of these high-energy neutrinos, we are beginning to sketch the first rough charts of the high-energy neutrino sky. It is a map of the universe's most violent and energetic precincts, drawn not with light, but with the paths of silent, ghostly travelers. Each one is a telegram from the edge of physics, telling us what happens when matter is pushed to its absolute limits. Buried beneath the polar silence, a cubic kilometer of ice has been transformed into a cosmic ear. This is the IceCube Neutrino Observatory, a monument to human ingenuity designed to listen for the whispers of the universe's most violent events. Its construction was a feat of Antarctic engineering. Engineers used a hot water drill to melt 86 holes, each over 2.5 kilometers deep, into the ancient, pristine ice. Into these abysses, they lowered strings of 60 sensitive light detectors, like pearls on a cosmic necklace, creating a three-dimensional grid that encompasses over 1 billion tons of ice. This frozen volume is the detector itself. The method relies on catching the faint, ethereal blue glow of Cherenkov radiation. When an ultra-high-energy neutrino on its trillion-to-one journey finally interacts with an atom in the ice, it can create a secondary particle like a muon that travels faster than light can move through the frozen medium. This creates a cone of blue light, a shock wave that expands through the crystal-clear ice. The thousands of embedded digital optical modules wait in the absolute darkness, their golden eyes staring into the void, ready to capture the precise nanosecond this blue flash passes by. By timing the arrival of this light at different sensors, physicists can trace the neutrino's path back to its origin in the sky with astonishing precision. For years, IceCube detected these high-energy ghosts, but their sources remained a mystery. Then, in September 2017, an alert went out. IceCube had caught a single, tremendously energetic neutrino. Its trajectory pointed like a celestial arrow back to a distant monster, a blazar known as TXS 0506 plus 056, blazing 4 billion light-years away. A blazar is the heart of an active galaxy where a supermassive black hole is actively feeding, and by a sheer cosmic coincidence, one of its powerful jets of plasma is pointed directly at Earth. This alignment makes them appear incredibly bright across the electromagnetic spectrum. When IceCube's coordinates were shared, telescopes around the world and in space swiveled to look. They found the blazar in a state of extreme flaring, emitting enormous amounts of gamma rays. This was the smoking gun, for the first time, humanity had identified a likely source of high-energy cosmic neutrinos. This single ghostly particle, after traveling for 4 billion years, had delivered a message confirming that the violent engines of supermassive black holes are powerful enough to accelerate protons and create these elusive messengers. It was a landmark moment, opening a new window onto the high-energy universe, one built not with light but with shadows. The same ghostly nature that makes neutrinos so difficult to catch also makes them a prime suspect in the hunt for dark matter. For decades, astronomers have known that galaxies rotate too fast to be held together by the gravity of their visible stars and gas alone. Something invisible, a vast halo of dark matter, must provide the extra gravitational glue. The identity of this missing mass is one of cosmology's greatest puzzles, and neutrinos, the ultimate phantoms, seem like a natural fit. After all, they are abundant, invisible, and everywhere. Yet there is a fundamental problem. The 3 neutrinos we know and love are what cosmologists call hot dark matter. They are born with such high energy that they travel at nearly the speed of light. This incredible velocity is their undoing as a dark matter candidate. If dark matter were made of these speedy, lightweight particles, its gravitational influence would be too spread out. It would prevent the clumping of matter needed to form the very first galaxies. The cosmic structures we see today, the vast web of galaxy clusters and filaments, could never have coalesced from a universe filled with such fast-moving stuff. It would be like trying to build a sandcastle in a hurricane. The grains would be blown away before they could stick together. So if not the standard neutrinos, then what? The search turns to a more sedentary ghost. This is where the hypothetical sterile neutrino re-enters the story. Unlike its energetic cousins, a sterile neutrino could be substantially heavier and, crucially, much slower. It would be cold, dark matter. Because it does not interact through the weak force, it would be born with very little kinetic energy, moving sluggishly through the nascent universe. This slowness would have been the key to structure formation. These heavy, slow-moving ghosts would have clumped together easily under gravity, creating the gravitational seeds around which ordinary matter could gather, eventually lighting up as the first stars and galaxies. Their sheer abundance and mass could account for the invisible halos we detect around every galaxy. Imagine a cosmic dance where the visible stars and gas are just the few dancers you can see under a spotlight, while the entire ballroom floor is packed with invisible partners, the sterile neutrinos guiding their every move. The evidence for this is still circumstantial but compelling. Certain unexplained astronomical observations, like a mysterious glow of X-rays from some galaxy clusters, could be the signature of a sterile neutrino decaying in the depths of space. Experiments are now being designed with unprecedented sensitivity to hunt for this decay line, a faint fingerprint in the X-ray sky that would confirm the existence of this ultimate phantom. If found, it would solve 2 profound mysteries at once, revealing that the ghost we have been chasing and the dark matter shaping the cosmos are 2 faces of the same invisible entity. These silent conversations between matter and antimatter may soon be recorded in unprecedented detail. The next generation of neutrino observatories are not just upgrades, they are leaps into the unknown, designed to capture the subtlest whispers of these cosmic phantoms. In the United States, a monumental project is taking shape. The Deep Underground Neutrino Experiment, or DUNE, will fire the most intense beam of neutrinos ever created straight through the Earth. Their journey will begin at Fermilab near Chicago, where protons are smashed into a target to produce a pure, focused stream of neutrinos. This beam will then travel straight through 800 miles of rock, emerging at the Sanford Underground Research Facility in South Dakota. There, waiting a mile underground, will be 4 colossal detectors, each filled with 17,000 tons of liquid argon. This technology is a revolution in itself. When a neutrino interacts in the ultra-pure, frigid argon, It creates a spray of electrons that leaves a detailed, three-dimensional image, like a photographic plate at the atomic scale. This allows scientists to reconstruct the interaction with breathtaking precision, watching the oscillation from one flavor to another in real time as the neutrinos journey through the planet. Dune's primary mission is to hunt for the ultimate prize, the difference in how neutrinos and antineutrinos oscillate. This tiny asymmetry, known as CP violation, could be the very reason our universe is made of matter. If Dune finds that neutrinos and their antimatter counterparts behave differently, it would provide a compelling explanation for how a universe of pure energy ended up with galaxies, planets, and life. Simultaneously, on the other side of the world, Japan is building a behemoth, Super-Kamiokande, and will be the successor to the legendary Super-K, a cylindrical tank of ultra-pure water so vast it could hold 10 Olympic-sized swimming pools. Its walls will be lined with 20,000 hypersensitive light detectors, creating a total volume more than 5 times larger than its predecessor. This immense size gives Super-K a dual purpose. It will study atmospheric and beam neutrinos with unparalleled statistics, nailing down the precise parameters of their oscillations. But its sheer scale also makes it a perfect sentinel for the heavens. It will be the ultimate supernova watchtower. If a star explodes in our own Milky Way galaxy, Super-K would not detect just a couple dozen neutrinos as it did in 1987. It would catch tens of thousands. This rich, detailed data stream would be a live broadcast from the heart of a collapsing star, revealing the intricate physics of the explosion millisecond by millisecond. Together, Dune and Super-Kamiokande represent a new era. They are not just looking for answers, they are building the instruments that will write the next chapter of our cosmic story, using the universe's quietest particles to answer its loudest questions. Hollywood has a habit of turning scientific subtleties into spectacular plot devices. In the 2010 film The Flash, for instance, a neutrino beam is used to create a superpowered villain, granting him immense strength and speed. Another science fiction series, Star Trek: The Next Generation, frequently used neutrino emissions to detect cloaked Romulan warships. These fictional portrayals take the neutrino's real, ghostly nature and amplify it into something we can easily see and weaponize, a beam of tangible power. The truth is far stranger and more wonderful. A real neutrino beam would be completely invisible and harmless, passing through your body, the entire planet, and the cloaked Romulan ship without a single interaction. The real magic of the neutrino is not in what it does, but in what it does not do. It refuses to fight, to be seen, or to be contained. This relentless intangibility is what makes its actual scientific discovery so much more compelling than any fiction. We did not find it by seeing a flashy beam, but by patiently counting a handful of transformed atoms in a vat of cleaning fluid over 30 years. The real story is not about harnessing its power, but about the quiet patience required to simply acknowledge its existence. These fictional tales, while fun, highlight a deeper truth. We are drawn to the neutrino because it represents the ultimate frontier, a piece of the universe that operates on rules so alien to our everyday experience that they feel like magic. The line between a ghost particle and a superpower is thinner than we think, drawn only by our growing understanding of the cosmos's quietest rules. This bizarre chameleon act is a direct window into the quantum world. Neutrino oscillation is not just a particle changing its clothes. It is a macroscopic, real-world demonstration of quantum mechanics in action over staggering distances. At its heart lies one of the strangest concepts in all of physics: quantum superposition. A neutrino born in the sun does not simply exist as an electron neutrino. From the moment of its creation, it exists in a blurred state, a simultaneous combination of all three flavors at once. It is an electron neutrino, a muon neutrino, and a tau neutrino all at the same time. This is not a rapid switching, but a fundamental state of being. Think of it as a spinning coin that is both heads and tails until the moment you catch it and look. For the neutrino, its journey through space is that constant spin. Only when it finally smashes into an atom inside a detector like Super-Kamiokande and is its identity forced to choose a single state, collapsing from a blur of possibilities into one concrete flavor. The probability of which flavor it reveals is dictated by how far it has traveled. This is why the 8-minute journey from the Sun creates a specific mix of flavors upon arrival, a mix that Ray Davis' experiment was not equipped to see. His detector was not broken, it was just asking a question that the universe could only answer in a quantum way. This leads to an even deeper layer of weirdness: quantum entanglement. When multiple neutrinos are produced together in a single event, like in a nuclear reaction or a supernova, they can become inextricably linked. Their fates are intertwined so that measuring the flavor of one instantly influences the state of the other, no matter how far apart they have traveled. This spooky action at a distance, as Einstein called it, means the entire system of neutrinos from a single stellar collapse could be acting as one connected quantum entity, a ghostly network stretching across light years. We are witnessing a quantum effect playing out on a cosmic stage. The oscillation of a single neutrino from the Sun is a quantum process that begins at a nuclear scale and completes its journey over 93 million miles. This makes neutrino oscillation one of the largest quantum experiments ever observed. It takes a bizarre, counterintuitive rule of the tiny and projects it across the vast emptiness of space, forcing us to accept that the universe at its most fundamental level is not a collection of tiny billiard balls, but a tapestry of probabilities and interconnected waves. The ghost is not just a particle, it is a walking, talking paradox of quantum reality. This unruly tenant has been causing trouble since the day it moved in. The standard model of particle physics is our most precise and successful map of the subatomic world, a triumph of human intellect that neatly categorizes all the known fundamental particles. It has the quarks that build protons and neutrons, the force-carrying particles like the photon for electromagnetism, and the electron with its heavier cousins, the muon and the tau. For decades, everything in this elegant zoo had a clear, logical place, and then there are the neutrinos. They fit, but only if you ignore the mess in the corner. The original, pristine version of the standard model required neutrinos to be massless, just like the photon. This was a beautiful, symmetrical idea. But the discovery of neutrino oscillation smashed that requirement to pieces. We now know with absolute certainty that neutrinos do have mass. This single, stubborn fact is like an unruly tenant who has knocked down a load-bearing wall in a perfectly maintained building. The entire structure is still standing, but everyone knows a fundamental repair is urgently needed. The tiny mass of the neutrino is not just a small detail. It is a screaming anomaly that points to a vast, unknown territory lying just beyond our current understanding. So how do we explain this? How do we fit a square peg into a round hole without breaking the peg? Theorists have proposed some ingenious, if speculative, solutions. One of the most compelling is called the seesaw mechanism. Imagine a playground seesaw. On one end, you have a very light child, our familiar featherweight neutrino. On the other end, to balance it out, you would need an incredibly heavy child. The seesaw mechanism proposes exactly that. It suggests that for every light neutrino we see, there exists a hypothetical, monstrously heavy partner neutrino. This heavy neutrino could be billions of times more massive than any particle we have ever detected. The sheer weight of this hypothetical particle, pulling down on its end of the quantum seesaw, naturally explains why our known neutrino is so impossibly light. This is not just a clever fix, it is a gateway. The existence of such heavy neutrinos is a direct prediction of theories like grand unification, which aim to merge the electromagnetic, weak, and strong nuclear forces into a single, fundamental framework. These heavy partners would have existed only in the first moments after the Big Bang, decaying away almost instantly, but their brief existence could have been the very process that generated the matter-dominated universe we live in through leptogenesis. The ghost we struggle to detect today might be the faint, lightweight echo of a cosmic giant whose actions determine the fate of everything. Solving the mystery of the neutrino's mass is not about patching an old theory. It is about receiving a whispered invitation from the universe, one that asks us to step through a door and into a much grander, more complete picture of reality. This global hunt for ghosts is a symphony of international cooperation. From the ice of the South Pole to the depths of Japanese mines, a network of detectors works in concert, creating a web of observation that spans the entire planet. These facilities are not rivals, they are partners, sharing data in real time to achieve a common goal. Their collective power transforms them into something greater than the sum of their parts, a single, planet-sized observatory. This collaboration becomes critical when the universe decides to put on a show. Imagine a star collapsing in a distant galaxy. As its core implodes, it releases a tremendous pulse of neutrinos that radiates outward in all directions. These ghostly messengers travel at nearly the speed of light, and when they reach Earth, they do not strike just one location. They shower the entire planet simultaneously. This is where the global network proves its worth. A single detector like Super-Kamiokande and in Japan might register a handful of interactions. At the same moment, the IceCube detector at the South Pole would see its own set of flashes. Borexino in Italy and the Sudbury Neutrino Observatory in Canada would also record their own unique data. By combining the precise timestamps from all these locations, scientists can perform a feat of cosmic triangulation. The infinitesimal differences in arrival times, mere milliseconds apart, allow them to trace the paths of the neutrinos backward and pinpoint the exact location in the sky where the explosion occurred. This is not just about finding a point on a map, it is about creating a universal early warning system. The neutrinos from a core collapse supernova arrive hours before the light of the explosion does. So the moment this global network detects a coordinated neutrino burst, it can send out an instant alert to astronomers worldwide. Telescopes on every continent and in space can then swivel to that precise patch of sky, waiting to capture the very first moments of the supernova's light as it finally breaks through. We are no longer just building detectors, we are giving the entire astronomical community a new set of eyes, allowing them to witness the death of a star the moment the universe itself announces it. Most of the missing neutrinos were never truly gone. They were simply wearing a disguise. The great Solar Neutrino Problem was solved by one of the most bizarre phenomena in physics, the constant, chameleon-like shifting of a neutrino's identity as it travels. A particle born in the Sun as an electron neutrino does not remain one for long. It oscillates, flickering between its muon and tau forms, and detectors like Ray Davis's, built to see only one face, registered the others as absent. This revelation proved they have mass, shattering a key part of the standard model and opening a new chapter in physics. We now understand that the trillions of solar neutrinos flowing through you every second are a constantly changing mix of all three flavors. The core mystery of their disappearance has been solved, yet this answer only leads us to deeper, more profound questions. The hunt for the cosmic neutrino background, the faint whisper from the Big Bang itself, continues. These ancient ghosts are so quiet and cold that our current technology is deaf to them, a silent sea of particles we know must exist but cannot yet hear. And the tantalizing possibility of a fourth, sterile neutrino, a phantom that interacts only with gravity, remains a compelling enigma that could explain everything from particle physics anomalies to the very nature of dark matter. So while we have found the Sun's missing ghosts, the universe's oldest and most elusive phantoms are still out there, waiting for the next generation of detectors to finally tell their story. The greatest discoveries in this cosmic detective story may still lie ahead. From a ghostly deficit in a South Dakota mine to the quantum dance of cosmic chameleons, our journey through the neutrino mystery reveals a universe far stranger than we once believed. These particles, once thought to be silent phantoms, are now understood as vibrant messengers, constantly shifting their identities as they cross the cosmos. Their story is a profound reminder that the most fundamental truths about our universe are often hidden in plain sight, carried on the faintest of whispers. The very elusiveness of the neutrino is what makes it so invaluable, a pristine courier from the hearts of stars, the dawn of time, and the most violent explosions in the cosmos. This entire detective saga, from the Solar Neutrino Problem to the confirmation of oscillation, underscores a beautiful truth: solving one mystery simply unlocks the door to the next. Our map of reality is forever being redrawn by these silent travelers. The next chapter of this story is being written right now, in real time, by scientists peering into vats of liquid argon and listening to the Antarctic ice. The hunt for the cosmic neutrino background, the search for sterile neutrinos, and the quest to understand their role in the matter-antimatter asymmetry are the new frontiers. This is not a closed book but an ongoing exploration, and you have a front row seat. Stay curious, follow the announcements from laboratories buried deep beneath the mountains and from telescopes frozen at the bottom of the world. The universe's greatest secrets are still flowing through you, waiting only for us to learn how to listen.